On a calm, clear, chilly Monday night, March 26, 2024, the Francis Scott Key Bridge that allows Interstate 695 to cross the Patapsco River was undergoing repairs to potholes by an 8-person road crew, an operation performed at night while traffic volume was low. The MV Dali, a Neo-Panamax or New Panamax size 95,000 gross ton container ship, had left its berth around 12:36 a.m. Monday night/early Tuesday morning and was underway transiting the Fort McHenry ship channel toward Chesapeake Bay. Quote, about a minute after the Dali first lost power, one of the ship's 2 pilots contacted a shoreside dispatcher to notify them of the emergency and instruct them to close the key bridge to traffic. Police officers from the Maryland Transport Authority, or MDTA, were stationed on both ends of the bridge conducting traffic control duties as part of the ongoing maintenance project. The officers immediately stopped all traffic from entering onto the bridge. All vehicle traffic had been cleared successfully, just as the Dali neared the bridge in the ship channel. However, along the bridge's deck, performing maintenance and repairs was the road crew, 8 workers total, an inspector, and 7 maintenance crew members. Unaware of ship channel activity, most of the workers were on break inside their vehicles, waiting for their next load of cement. The maintenance trucks spread out along bridge spans 18 and 20. The inspector was performing his duties, walking the roadway on span 22, when suddenly, a crumbling thunder noise could be heard as the bridge started to shake. The MV Dali had lost propulsion control moments prior, at around 1:25 a.m., and slammed into Bridge Pier 17 at 1:29 a.m. From the NTSB, at a quote, estimated impact force over 4 times greater than that pier's lateral capacity, completely destroying it, subsequently causing the sudden and total collapse of bridge spans 17 through 22, roughly 3/4 of a mile of roadway. According to the NTSB, the inspector was able to run to safety, narrowly reaching span 23 as span 22, the one he'd just been occupying, disappeared behind him. The others were not so fortunate. This threw the remaining 7 road workers directly into the 48-degree water below, as the road surface fell nearly straight down out from under them. Trapped inside their vehicles, they were instantly beneath the surface amongst the collapsed wreckage, in approximately 50 feet of water, this being a deeper part of the bay, the cut for the ship channel. The massive container ship came to a stop as the scene was pure chaos all around. Law enforcement scrambled to assess the situation, and search and rescue crews worked tirelessly for hours, even days, in an attempt to rescue, assess, and recover any and all victims. Unfortunately, in the meantime, falsehoods, mischaracterizations, and blame game political theater took over much of the television and online media narrative immediately, albeit temporarily, all while those actually on the ground, working on site, investigators, local volunteers, families of the victims, parties directly involved, toiled, struggled, searched, and hoped for real answers. The ship's loss of propulsion and directional control would be found as probable cause, but contributing to the risk of, and in this case, total collapse. The NTSB also finding as a contributing factor, quote, the lack of countermeasures to reduce the bridge's vulnerability to collapse due to impact by ocean-going vessels, which could have been implemented if a vulnerability assessment had been conducted, as recommended by the American Association of State Highway and Transportation Officials. Similar issues pointed out in the NTSB's report with, quote, unknown levels of risk of collapse from a vessel collision, also present in other coastal and Great Lakes bridges across U.S. states like California, Delaware, Florida, Georgia, Illinois, Louisiana, Massachusetts, Michigan, New York, Pennsylvania, Texas, and more. In total, 1 crew member aboard the container ship Dali suffered a minor injury. Of those occupying the key bridge, the roadwork inspector escaped physically unharmed. One of the road workers inside a vehicle made a harrowing escape right as his vehicle entered the water and would eventually be rescued successfully, suffering serious injuries. And 6 of the remaining road workers who had fallen into the dark 48-degree waters below, trapped inside their vehicles, did not survive. primary source for this video is the NTSB's Marine Investigation Report, or MIR-25-40, Contact of Container Ship Dali with Francis Scott Key Bridge and subsequent bridge collapse, along with their supporting documentation, like interviews with those directly involved, nautical operation findings, and more, found in the NTSB's Key Bridge investigation docket. From the NTSB, quote, NTSB investigators were on scene at the initial incident command post at the Maryland Transport Authority's facility by 5:25 a.m. Formal determination of the accident as a major marine casualty was received by the U.S. Coast Guard at 7:33 a.m. The NTSB, according to its Memorandum of Understanding with the Coast Guard, was the lead federal agency for the safety investigation. Although several local and federal agencies were on scene that morning in the immediate aftermath for search, rescue, and recovery operations, the NTSB's report is used as a primary U.S. publication for findings, conclusions, and lessons learned. The U.S. Coast Guard's Marine Board page for the Dali incident, at least as of making this video, links back to the NTSB's reports stating, quote, in accordance with federal rules and agreements, the NTSB has overlapping jurisdiction with the Coast Guard in respect to conducting safety investigations for major marine accidents. In this case, the Coast Guard has convened a Marine Board of Investigation and is investigating. However, the NTSB was designated as the lead federal agency for the marine casualty to determine the cause of the accident. Please refer to NTSB's website on this accident to learn additional information on this matter. Unquote. Now, this is the type of page, when applicable, the final Coast Guard's report would be found when the Marine Board is also heavily involved in the investigation. At time of writing, the page also references the Unified Command Incident Response site at keybridgeresponse2024.com that served as a repository, quote, dedicated to the handling of Key Bridge Response 2024. If you're interested in more detailed reading on sites like response.maryland.gov, baltimorecity.gov, and DVIDs, for example, I'll link these all in our sources document. All other sources, references, and featured media, like Hyundai Heavy Industries' revised report, Chief McCoy's in-depth explanation as to the ship's loss of propulsion and control, Tim B. at Sea's input on potentially why tugboats were not escorting the Dali under the Key Bridge. Just a few examples, all of which and more, as always, will be linked in the description. But I've also been working to improve our video source material repository, migrating it all to our own website at brickimmortar.com/sources. Check it out if you're interested. The Francis Scott Key Bridge. Open to traffic on March 23, 1977, and originally known as the Outer Harbor Crossing, the Francis Scott Key Bridge was a continuous steel through truss bridge, built by Maryland Transport Authority over a period of roughly 5 years to when it opened in 1977. The superstructure of the bridge would be designed using non-redundant steel tension members, or NSTMs, steel members formerly labeled by the Federal Highway Administration as fracture critical. In fact, I had actually named the original Brick Immortar bridge collapse playlist Fracture Critical. And for reference throughout the remainder of this video, we'll be referring to the Maryland Transport Authority as MDTA. The substructure of the bridge, quote, consisted of 2 reinforced concrete abutments at each end of the bridge and 36 vertical piers, 31 2-column rigid frame reinforced concrete piers, 2 rigid frame reinforced concrete piers, and 3 solid wall piers. These photos from the NTSB docket provide a closer look at pre-collapse abutments, piers, and continuous girders from underneath. The superstructure contained 34 bridge spans total. Bridge spans are those length of bridge deck and their supporting girders between piers. The primary portion over the ship channel, containing the through truss, was a total of 3 spans, half a mile long. At its highest point, the single largest span, span 18, directly above the ship channel was roughly 185 feet above the waterline. This span alone was roughly 1,200 feet long, from Pier 17 to Pier 18. There were 4 lanes of traffic total, 2 carrying traffic south-southwest and 2 going north-northeast, which for the purposes of this video we'll refer to going forward as simply southbound or northbound, respectively. Northbound and southbound lanes were divided physically by what appears to be concrete jersey barriers, along with only a foot or two worth of shoulder space on either side. Average drive time over the bridge between each abutment, roughly 1 3/4 miles from end to end, at the posted speed limit of 55 miles per hour, was just under 2 minutes. During 2023, the year prior to collapse, the NTSB states, quote, "The annual average daily traffic was 34,121 vehicles per day, and the percentage of trucks on the bridge was 10%. Brick Immortar takes no sponsors, employs zero AI tools in any aspect of the making of these projects, and allows zero outside influence into our in-depth research, script writing, and video creation process. To support this channel, liking, subscribing, and sharing are a huge help. Or check out patreon.com/brickimmortar, brickimmortar.com, or click that join button on YouTube. Immortar supporters understand the effort that goes into these productions, and their support literally makes this channel possible. I was incredibly inspired when I made my first actual maritime photo sales last year, actually, and I had a few more waiting to put on the store that I was reluctant about. But after those first metal print sales, I decided to finally give it a go, and published several more of my photos on the store from my travels. And as always, I purchased my own merch to give it a quality control check, and these really passed the test. I really like these. We're also celebrating this channel hitting 5 massively successful years as of March 2026. So a huge thanks to you, the viewer, and to our supporters for helping this channel continue. Thank you, and don't forget, your safety matters. Motor Vessel Dali. The MV, or Motor Vessel Dali, a 984-foot long, 158-foot wide Neo-Panamax class container ship, built in 2015 by HD Hyundai Heavy Industries Company Limited in Ulsan, South Korea, was of Singapore flag, or registry. And for reference, we'll be referring to HD Hyundai Heavy Industries Company Limited as simply Hyundai for the remainder of this video. Owned by Grace Ocean Pte. Limited and operated by Synergy Marine Pte. Limited, this massive vessel was capable of carrying just under 10,000 containers total, based on 20-foot TEU size and depending on configuration, or deadweight of just under 117,000 metric tons. Deadweight is the weight of, essentially, everything a ship can safely carry, like cargo, fuel oil, fresh water, ballast water, provisions, passengers, and crew. The vessel had a draft, on the day of, roughly 40 feet deep. The Dali contained 2 superstructures, or the structures that rise above the main deck. The forwardmost structure, or forward house, located nearly amidships, contained the flying bridge and the navigation deck, or wheelhouse, both at the top, and decks A through G were crew accommodations. Superstructure number 2, the aft house, nearly astern, or toward the rear of the vessel, was mostly housing for the engine exhaust, or stack. Below the structure was the primary engine room, diesel power generators, the engine control room, electrical transformers, breakers, and automation networking, or switchboards as the NTSB refers to them. Vessel propulsion was provided by a diesel-powered 55,626 horsepower Hyundai MAN B&W super long-stroke 9-cylinder engine connected directly to a, quote, single 6-blade fixed-pitch propeller with a diameter of 30.5 feet. Steerage was provided by a single rudder, which required enough water moving past it to be effective, meaning if the ship was extremely slow or stopped, the rudder had little to no effect, and thus, slow-speed steerage and positioning was aided by a bow thruster. From the NTSB, quote, according to vessel documentation, the Dali's bow thruster was not effective at speeds greater than 5 knots, something crucial to keep in mind. Electrical power was provided by, quote, 1 or more of 4 alternating current diesel generators. At least one generator had to be operating and supplying the vessel with power for the ship's main engine to run. Diesel generators 1 and 4 were rated for 4,320 kilowatts, and generators 2 and 3 for 3,840 kilowatts. These generators and their high voltage output were what ultimately provided power for the vessel's high and low voltage needs. The 6,600 volt AC power these generators provide is stepped down via 2 transformers for redundancy to 440 volt AC power. Each transformer was gated by breakers on either side, high voltage breakers on the generator side and low voltage breakers on the other. And from the NTSB, the vessel also, quote, had an emergency diesel generator, or EDG, which was independent from the other generators, a 200 kilowatt, 440 volt AC 3-phase generator driven by a 6-cylinder, 330 horsepower diesel engine. The EDG would activate automatically during a loss of normal low voltage power, or blackout, and provide power to only the emergency switchboard, which powered essential onboard systems such as navigation, communication, and emergency lighting. However, the EDG alone does not produce enough electrical power to operate the auxiliary pumps to run the main engine. According to the vessel's captain, the Dali saw ports in recent months like Sri Lanka, Malaysia, multiple ports along China's coast, South Korea, through Panama, Oman, and its routine on the U.S. East Coast saw it stop in ports like Newark, New Jersey, Norfolk, Virginia, and of course Baltimore. Much like those massive car-hauling, roll-on, roll-off, or ro-ro vessels, these container ship loads are another example of the logistics challenge to maximize the space on board with paying cargo and avoid as much as possible any deadheading. At least that's what we'd call it when I was in the logistics industry. Deadheading in this instance, put simply, means the movement of a commercial vessel without carrying paying cargo or passengers. And more specifically to a vessel like the Dali, the lack of paying cargo, filling out all those spaces available within the vessel's cargo capacity, means any spaces or carrying capacity left empty aren't generating as much revenue as when they're filled whenever the vessel's underway. Where this gets even more complicated, but stick with me because it will make sense in just a bit, is that these vessels don't simply fully load to max capacity and then fully offload at their destination. Just like in our video on car carrier Golden Ray, I'll have a link in description if you're interested later. I liken it to the simplified analogy of an LTL or less than truckload tractor-trailer setup, only on a much larger scale. If you book a dedicated truckload, it's called, for example, of say 28 pallets of expensive electronics bound for a single department store, that trailer's entire space will be dedicated just to that load, fully loaded at the point of origin and then fully offloaded at its destination, with the trailer doors ideally locked and sealed to ensure no tampering along the way. Now, if I book a load for say 3 pallets of inexpensive clothing going to that same department store location, we certainly don't want to pay for the entire 53-foot trailer, but we also don't have 25 more pallets to fill that remaining trailer space with. But in the business-to-business world of logistics and supply chain, fortunately there are companies that specialize in combining smaller loads to try and fill out their trailers, maximize their cargo space with various orders of different sizes, in hopes to deliver in a nearby radius of multiple businesses with less than truckload or LTL orders. But with a vessel like the Dali, there are several more layers of complexity. Total allowable weight plays a major role, along with where it can be positioned on the vessel. In fact, the cargo containers you see above deck on a ship like this are only half the story. These ships have nearly as many container spaces below deck as there are above. Referred to as a bay, if we look for example at Bay 01, found in the NTSB documents. Here we can see the ship's deck line, and this cross-section shows the amount of containers and their positions above and below. In Bay 01, those container racks below decks are fewer, in order to follow the contours of the inner hull. But if we look at Bay 09, or Bay 15, or even further aft at Bay 39, the load plan begins to maximize the allowable space inside the hull below decks. Whereas by contrast, the sternmost Bay 68, just above the steering gear and likely the aft mooring deck, this one can't utilize any space below and has racks for containers only above decks. Just something I find interesting in how these ships maximize their enormous amount of space for transporting cargo, from a former logistics manager point of view. Anyway, taking a look at this load plan, we can see the Dali at the time of the incident carried many empty containers as well, At each port, each charterer will also exchange empty containers as part of their typical load/unload process. In addition, if a group of loaded containers is, say, extremely heavy, but amongst many that are not, the load must be evenly distributed between port and starboard, and, to an extent, bow and stern. Now, if we go back to that less than truckload or LTL analogy from earlier, we can see the Dali in this instance, and quite commonly aboard ocean-going container ships of similar size, is carrying anything from electric motors to waste paper, soybeans, mayonnaise, machinery, to aluminum scrap. The cargo load is an incredibly complex assortment of various orders the load planners will use in an attempt to maximize usage of the paid cargo space between ports. Add to that, some containers will also be refrigerated, requiring power from the vessel to maintain their internal temperature. In the industry, these are referred to as reefers, or reefer containers, or on the road, reefer trailers. Crucial to this incident, and common aboard these vessels, was a handful of containers with potential hazardous material risk, like lithium-ion batteries, perfumes, household chemicals, fuel and lubricants, alcohol, copper powder, and more. More importantly, these in particular I've listed off were loaded up near the bow area. Baltimore Harbor. The primary shipping lane, Fort McHenry Channel, along this portion of the Patapsco River, is the pathway large vessels must take in or out of the harbor underneath the Francis Scott Key Bridge to and from Chesapeake Bay. Key Bridge physical protections included, quote, 4 dolphin structures, each with rubber fenders, and crushable concrete and timber fendering systems around Pier 17 and Pier 18, in place since the bridge opened in 1977. Dolphins 1 and 2, those on the north side of the bridge, were roughly 489 feet offset from each pier, respectively, with presumably Dolphin 1 intending to protect Pier 17 and Dolphin 2, Pier 18, from ships approaching north to south. Quote, each dolphin was composed of 25.46-foot diameter driven steel sheet pile ring filled with concrete and a 28-foot diameter reinforced concrete cap. Each concrete cap, the part you can see above the waterline, was partially surrounded by hanging rubber fenders. Attached and surrounding Pier 17 and 18 were, quote, crushable concrete fender systems, composed of hollow, thin-walled concrete box structures attached to the piers. The timber fender, which was composed of vertical 6 by 12 inch, 12 by 12 inch, and 14 by 16 inch, and horizontal 12 by 12 inch timber members in a grillage geometry, was attached to the outer face of the concrete box fender. Timber fenders are frequently used for bridge protection because of their relatively low cost and good energy absorption characteristics. In accordance with the National Bridge Inspection Standards, the Key Bridge and its pier protection systems were subject to regular safety inspections by nationally certified bridge inspectors. According to the Federal Highway Administration, inspections are necessary to maintain safe bridge operation and prevent structural and functional failures. The Key Bridge's most recent inspections in March 2021 and May 2023 found the condition of the deck, the superstructure, and the substructure as being in satisfactory condition, and the pier protection was rated as in place and functioning properly, unquote. Monday, March 25th, 2024. Moored at the Seagirt Marine Terminal in Baltimore Harbor, the Dali was undergoing final cargo operations. Throughout the day, the Dali's crew was also, quote, performing in-port maintenance in advance of that evening's planned departure. While working on the diesel engine exhaust scrubber system for Diesel Generator 2, the only generator supplying power to the vessel at that time, a crew member mistakenly closed the inline engine exhaust damper, which effectively blocked the engine's exhaust gases from traveling up its stack and out of the vessel. The blockage caused the engine to stall and slow down, preventing Diesel Generator 2 from generating sufficient high-voltage power. Sensing this underperformance, the vessel's power management system opened, or tripped, the online generator's main breaker, resulting in a loss of high-voltage power. This also tripped other crucial breakers downstream, cutting low-voltage power, causing a full vessel blackout. When power was restored, certain auxiliary pumps restarted automatically according to their design. The flushing pump, which was being used to supply fuel for the diesel generator that had just come online, required a manual restart as designed. The generator ran for about 5 minutes before the crew could manually restart the flushing pump. The generator's speed began to decrease due to insufficient fuel pressure. The decrease in speed caused it to underperform, preventing it from generating sufficient power, tripping the generator's breaker again, resulting in a loss of high voltage power, causing the second full vessel blackout of that day. The NTSB continues. In the meantime, the crew had reopened the engine exhaust damper manually. Diesel generator 2 automatically restarted and connected to high voltage power. Generator 2 was able to run by consuming residual fuel in the supply lines. While recovering from this second blackout, the electrician closed the high and low voltage breakers that had been tripped. Closing the breakers powered the low voltage switchboard, which restarted the fuel pumps for diesel generators 1 and 2 automatically. The affected transformer and its associated breakers remained in use when the ship departed the Seagirt terminal that night. And we will cover the relevance of these in-port blackouts during the investigation segment later in the video. Monday night. From the NTSB. On the evening of March 25th, cargo operations were completed at 11:06 p.m., and the crew of the Dali, 21 crew members, were preparing the vessel to depart from Seagirt Marine Terminal to begin a 27-day transit to Colombo, Sri Lanka. The vessel was loaded with 55,671 metric tons of cargo within 4,679 containers, or the equivalent of 8,544 20-foot units, or TEU. These containers were mostly 40-foot long, though, with 20-footers dispersed throughout. At 12:36 a.m. Tuesday, March 26th, on watch in the wheelhouse were the ship's captain, a highly experienced ship's master with 19 years holding the title and 5 months aboard the Dali, the second mate with just over 10 years experience as second mate on similar vessels, 8 months aboard the Dali, and currently at the helm was an AB with 3 years seafaring experience, about 5 months aboard the Dali. In addition to the bridge crew, there were 18 more crew members throughout the ship, all in the employ of Synergy Marine Pte. Limited. Also in the wheelhouse were 2 harbor pilots that came aboard just prior to departure. An Association of Maryland senior pilot was aboard to command the vessel navigationally through the harbor, along with a pilot in training to shadow and partake in this process. In total, there were 23 souls on board. Prior to handing navigational command of the vessel over to the pilot, the captain stated, "We tried all the engines, and then we tried out the bow thruster. Everything was working. Everything is in operational condition." And the master pilot exchange card signed and dated 26th of March 2024 reflects this as well. For example, in the section, "Equipment checked and ready for use," quote, "Anchors, yes. Steering gear, yes. Bow thrusters, yes. Engine telegraphs, yes." And further down in section C, "Navigational warnings affecting the transit," was indicated, quote, "No warnings affecting the transit." Along with the equipment operational defects and ECDIS backup procedures in use indicated, quote, "All equipment's in good working order." The captain also noting he had no concerns in the pilot's abilities, and their interactions on the ship's bridge together were, quote, "Very professional, very friendly, good communication." The captain remaining fully present and on watch, regardless of the pilot's navigational command. All seemed normal as the Dali initially got underway, pushing off from the Seagirt terminal pier with the assistance of 2 tugs, ultimately bound for Colombo, Sri Lanka. The senior pilot stated, quote, "I went through the master pilot exchange with the master. He told me everything was in good working order. The tug Eric McAllister and the tug Bridget McAllister were assigned to assist the MV Dali undocking. I directed the Eric to get a line up to the port shoulder and the Bridget to get a line up to the port quarter. Last line was at 12:36 a.m. I then had the tugs back to breast the MV Dali off the face of the pier approximately 175 feet. We then proceeded on dead slow ahead out the grain elevator channel. I stopped the tugs. I kept the Eric alongside with the line up. I let the Bridget go. I told the Eric to back easy on one bell to control the speed of the ship. Presumably, grain elevator channel here is likely the pilot referring to the Seagirt Marine Terminal West Channel, as it runs directly in front of these bulk loading piers, which contain what appears to be two separate operations, one for coal and the other looks like grain barge operations, with the voyage data recorder or VDR playback backing this up. Again, at this time, all seemed normal, the NTSB stating, the senior pilot called the Bridget McAllister at 1:06 a.m. on VHF and said, "Bridget, I like my chances if you want to take off." The tug operator/captain wished them a safe trip, reduced speed, and soon after altered course to starboard to start heading northwest in the Fort McHenry Channel. At 1:07 a.m., the senior pilot contacted the Eric McAllister to coordinate the tug moving under the line to be let go by the crew forward. The tug recovered their line at 1:08 a.m. and increased speed to move away from the Dali on a southeasterly heading. Also, at 1:08 a.m., the senior pilot ordered a slow ahead bell on the engine. The mate on watch repeated back slow ahead, and the throttle was moved accordingly. The master contacted the bow via UHF radio to notify them that only one person needs to remain forward. The ship's captain stating, quote, "Once we did the first turn, to my best recollection, we let go the aft tug. We cast off the aft tug. Then once we turned full and were in the channel, outgoing channel, at that time we cast off the forward tug also." With the VDR playback and X-band radar screenshots confirming that by roughly 1:09 a.m., both tugs were let go and parting ways with the Dali. Quote, at 1:11 a.m., the helmsman stated heading 140 to indicate to the senior pilot and bridge team that he was steady on the course. The Dali was on a heading of 141.0 degrees, making good 142.1 degrees at a speed of 4.4 knots. After a quick discussion, the pilot in training took the con at the liberty of the senior pilot and ensured the helmsman was aware of the con change by confirming the current heading, maintain of 140 degrees at 1:13 a.m. The Dali was on a heading of 140 degrees, making good 139.4 degrees at a speed of 5.8 knots, and had a 1.4 degree per minute rate of turn to starboard at this time. Now, heading versus making good, to simplify, refers to the heading or direction the ship's pointed versus the direction the ship is actually traveling. All vessels have inertia on the water, and a vessel this size has a massive amount, especially as it gains momentum. Thus, if the steering input is physically made, say, via the rudder, and the bow even comes around to match it, the vessel will take time and distance to actually change its path from that previous course to its new intended heading. It's also difficult to perceive in a vessel of this size without instrumentation. A much more exaggerated example of heading versus making good are aircraft crosswind landings. It can appear very clear to the viewer that the aircraft is pointed in a completely different direction as it approaches where the wind is blowing at an angle across the runway. But the path it's actually traveling, or making good, follows the direction of that runway's heading. The NTSB continues. The center line of the ship was about 88.6 feet to port of the channel's geometric center. Tug Eric McAllister was about 0.5 nautical miles away, continuing to head east at a speed of 9.5 knots. At 1:14 a.m., the pilot in training stated 141. The helmsman repeated it back, and at 1:15 a.m. stated heading 141, sir, to convey that he was steady on 141 degrees. In the meantime, the senior pilot was working to calibrate their portable position beacons as an input to the portable pilot unit. The unit was receiving position data from the vessel's AIS plug, and it is customary to have an independent positioning source for redundancy and accuracy, hence the pilot's own portable unit. The pilot in training indicated that it was not necessary to troubleshoot it at this time, as he continued to safely and effectively con the vessel using the available resources. At 1:17 a.m., light music began to play on the Dali bridge. Shortly after, the pilot in training mentioned he had been on the sister ship, the Cezanne, on a previous trip in his training. The aft mooring station was secure for sea at 1:18 a.m. The pilot in training asked the senior pilot if he would like the vessel's engine ordered increased to half. The senior pilot said to keep it 10 knots or less. The pilots shared a casual conversation about a previous trip the senior pilot had completed. By 1:18 a.m., as the Dali progressed in the channel, according to the VDR playback, the Eric McAllister, the previously forward tug, shows roughly 0.6 nautical miles from the Dali, the distance appearing to increase, with the Bridget McAllister no longer on screen from what I can tell. On X-band radar playback, which is more noisy visually, and also shows time in UTC rather than local, so -4 hours in Eastern Daylight Time. The X-band playback appears to show both tugs depart and go their separate ways in somewhat clear images between 1:11 and 1:13 a.m. Just from this alone, we can tell the Bridget's distance from the Dali is even greater than the Eric McAllister. As the Dali made further progress through the bay, the container ship speed reaching around 8 knots, the routine, seemingly normal transit at 1:24 a.m. and 59 seconds was suddenly and surprisingly interrupted when, quote, "The MV Dali suffered a complete blackout. We lost engine power and all lights on the vessel went out," according to the senior pilot. At 1:25 a.m. and 14 seconds, the senior pilot asked, "Do we have steering?" To which the mate on watch answered, "We have steering." The senior pilot asked the helmsman directly, "Do you have steering?" At 1:25 a.m. and 16 seconds, to which the helmsman answered, "Yes, sir, yes, sir." 2 seconds later, the senior pilot gave the helmsman the command 141, and the helmsman repeated it back. The senior pilot instructed the helmsman to let him know if he could not steer. The master hailed the bosun on the UHF radio, instructing him to stand by and keep the bow stopper up, referring to the bow anchor stopper. At 1:25 a.m. and 30 seconds, the tone of the alarms on the bridge changed, and the master commanded the bosun to pick up the bow stopper. 17 seconds later, the helmsman stated, "Swinging to starboard, wheel on hard port, sir," to inform the pilots and bridge team that the vessel's heading was swinging to starboard and he had the maximum possible helm applied. The vessel was on a heading of 143.0 degrees, making good 141.7 degrees, at a speed of 8.6 knots, and had a 3.5 degree per minute rate of turn to starboard. Currently located where the Curtis Bay Channel joins Fort McHenry Channel from the west. At this time, the forwardmost point on the Dali was about 2,506 feet from the Francis Scott Key Bridge, roughly 2.5 ship lengths. First power recovery. At 1:25 a.m. and 51 seconds, there was a change in the alarm tone, followed by a sound similar to the automatic transfer bus switch activating. About 6 seconds later, this was 440 volt or low voltage power returning. The senior pilot contacted their association's duty dispatcher at 1:26 a.m., informing him that they lost steering and instructing him to have local authorities shut down the bridge. The dispatcher verified that the senior pilot was referring to the Key Bridge, and the 9-second phone call was ended. The NTSB continues. The helmsman informed the senior pilot the vessel was swinging to starboard at 1:26 a.m. and 10 seconds. The senior pilot immediately ordered the helmsman port 20. The vessel was on a heading of 144.5 degrees, making good 143.2 degrees at a speed of 8.5 knots, and had a 5.7 degree per minute rate of turn to starboard. It was about 2,132 feet from the Key Bridge, closing at a rate of 14 feet per second. While the helmsman was executing the helm order, the senior pilot instructed the pilot in training to grab my radio, get to channel 14, and then to grab a Mac boat. The senior pilot asked the master if the bosun was standing forward at 1:26 a.m. and 30 seconds, and the master confirmed that he was. The helmsman confirmed that the wheel was on port 20 at 1:26 a.m. and 35 seconds, as the pilots used channel 14 to hail the McAllister tugboats. The call to the tugboats was placed at 1:26 a.m. and 38 seconds, and the situation was explained briefly, the Eric McAllister responding, quote, "Copy that, we'll be right there," about 17 seconds later. However, quote, the Eric McAllister was 16,716 feet, over 3 miles away in the Fort McHenry Channel near Lazaretto Point. Meanwhile, the Association of Maryland Pilots dispatcher was informing the MDTA duty officer of the emergency and their need to stop all traffic on the Key Bridge. The Eric McAllister captain turned the tug around 180 degrees immediately, about 25 seconds later, and was bound for the Dali, roughly 1 minute after they were hailed, at a speed of 12 knots. Now, to cover 3+ miles at 12 knots would take roughly 15 minutes or more, and we will cover the harbor tug questions in more detail later. Second loss of power. At 1:27 a.m., the Dali's bow roughly 1,500 feet from the Key Bridge and closing rapidly. The senior pilot was heard shouting, "Port anchor," and 3 seconds later, the captain shouted over the UHF radio to the forward crew, "Forward let go port anchor, forward let go port anchor." The initial response to this from the forward station was, "Sir, I cannot." But according to the NTSB, the transmission became unclear after that. Around this same time, the helmsman was heard confirming, quote, "Port 20, sir," or attempting to steer 20 degrees to port. About 4 seconds later, the senior pilot instructed the pilot in training to make a sécurité call, meaning an urgent VHF call on channel 16, to all vessels and/or stations within range. At this time, quote, the second officer made an announcement on the public address system saying, Chief officer, let go port anchor forward." About 10 seconds later, the senior pilot shouted, "Hard port." The helmsman confirmed by shouting it back. The pilot in training then made that sécurité call at 1:27 a.m. and 25 seconds. About 10 seconds later, the helmsman stated, "Wheel on hard port, sir," as the vessel developed a rate of turn of 7.5 degrees per minute to starboard. At 1:27 a.m. and 42 seconds, the senior pilot shouted, "Captain, do we have a bow thruster?" The master replied to the affirmative, accompanied by the second officer also replying to the affirmative. The senior pilot commanded a full to port on the bow thruster at 1:27 a.m. and 46 seconds. The second officer executed the command on the bow thruster control knob. 5 seconds later, at 1:27 a.m. and 51 seconds, the master commanded the forward station to let go of the anchor, and the boatswain replied stating, "I tried to open the brake." At about 1:28 a.m. and 10 seconds, Dali's starboard bow crossed the boundary of the Fort McHenry Channel. The vessel began to ground in mud. The massive container ship was on a course of 156.3 degrees at a speed of 6.6 knots and had a 4.9 degree per minute rate of turn to starboard. The command to release the anchor was made once again by the master 16 seconds later and again about 20 seconds after that. Just a few seconds later, quote, the helmsman stated, "Hard port, sir," and the senior pilot confirmed by saying, "Great," then shouting, "Full bow thruster to port," at 1:28 and 57 seconds. The mate on watch replied, "No, it's not working." Around this same time, there was a sound similar to the anchor chain running. Speed was still 6.6 knots, and turn rate had reduced to 2.0 degrees per minute to port. The vessel's bow was now 95 feet from Pier 17 and roughly 8 feet deep in the mud, still pushing forward through it steadily, or soft aground. At 1:29 a.m. and 15 seconds, a sound similar to the collapse of the Key Bridge could be heard. The senior pilot instructed the pilot in training to call the Coast Guard 14 seconds later, and contact was established with Coast Guard Sector Maryland at 1:29 a.m. and 50 seconds. The senior pilot asked the master if anyone was injured up forward. The master asked the forward station if the anchor was released. The forward station confirmed it was done and had been released. Alarms continued sounding on the Dali's bridge. The Dali is thought to have made a dual impact near simultaneously as it struck the fender arrangement down low, potentially owing to the bulbous bow near the waterline, just as the upper portion of the starboard bow impacted Pier 17 directly, quote, about 20 feet above the waterline. The protective dolphin on this side of the channel where the Dali impacted had no role in slowing the massive vessel's momentum, as the rate of turn and trajectory allowed it to bypass the reinforced concrete and steel obstruction entirely. Quote, about 13 seconds after the initial impact, Pier 17 collapsed. Within seconds, the main spans 17, 18, and 19, piers 19, 20, and 21, and spans 20, 21, and 22 had collapsed. Atop the bridge deck. Sitting in his truck while on break, Jay, as we'll refer to him, was one of 7 road repair workers, subcontracted by MDTA to perform road surface repairs along the bridge deck. The crew having been there since 7 p.m. that night. We'll come back to Jay's perspective in a moment. All 7 crew members were sitting in their vehicles awaiting a load of cement, taking a break. There was a total of 7 vehicles present, related to the road work, parked along the bridge deck. The MDTA inspector's passenger vehicle, 3 pickups, and 3 stake trucks. Stake truck simply refers to those larger cargo vehicles with flatbeds that look like they have fencing around them. All 3 pickups and 2 of the stake trucks had work-related trailers attached to them. More specifically, the vehicles were parked in the following arrangement in the right lane, from north to south. Atop span 22, the inspector's car. Along span 20, one of the stake trucks with a crash attenuator attachment along with the pickup with the light tower trailer. And between piers 18 and 17, atop span 18, directly over the ship channel, were a stake truck without a trailer carrying traffic cones, a stake truck with a concrete mixer attached, and then 2 pickups, one with a generator attached, the other with another light tower attached. With the repair work temporarily halted and outside temperatures in the mid-40s Fahrenheit, the workers waited in the cabs of their work trucks. Meanwhile, the roadwork inspector, we'll refer to him as D, was walking the bridge deck verifying the progress of the crew's pothole repairs. Quote, while the other guys was on break, I walked back down to my car. When I got to my car, I started to hear a crumbling thunder noise, and I instantly ran away. I stopped, I turned around, and I see the entire bridge collapse. I called the foreman. Then I quickly realized everything. I was in shock just seeing what just happened. So then I called operations. When I called, I was so frantic, I just called in and just was talking to someone. Whoever answered, I just told them what happened. The inspector was able to run to span 23 before the total collapse of the span he was occupying just moments prior. He had called the Maryland State Operations Center to report the collapse. Just prior to all this, road worker Jay was sitting in his pickup when he felt the bridge shake. The truck was suddenly falling, then it was suddenly in the water. All 7 highway workers fell with the bridge spans into the water when the central spans collapsed. Quote, water started filling the truck cab, even with the windows closed. Jay was able to force the driver's side window down while underwater and exit through the downed window. He then swam to the surface and continued to swim to safety. Along the way, Jay found a piece of metal he was able to float on, waiting to be rescued. Search and rescue. Within seconds of the impact and collapse, the pilot in training called the U.S. Coast Guard to notify them of the incident and the possibility of people in the water. At 1:33 a.m., quote, the senior pilot asked the mate on watch, is your crew up forward safe? The forward station communicated, we are luckily safe, sir. We have come aft. About 1:34 a.m., the Coast Guard issued an urgent marine information broadcast requesting assistance from passing traffic. The tug Eric McAllister, already contacted by the senior pilot about 3 minutes prior to impact, was the first vessel on scene, arriving at 1:40 a.m. 2 other tugs, the Bridget McAllister and the Timothy McAllister, arrived soon after. Baltimore Harbor fell under the area of responsibility of Coast Guard Station Curtis Bay, which was located roughly 4.1 nautical miles away on the water. The incident scene within reach, physically now, by boat only, the road having collapsed and large power lines so close by, running parallel to the bridge. Sunrise would be several hours away, around 7 a.m., so first responders would also be up against the darkness, on top of such a chaotic, tangled mess above and underwater. Earlier, road worker Jay, quote, swam to nearby debris and floated there. The first Coast Guard boat, a Station Curtis Bay response boat medium, was underway within 10 minutes. Unit CG-45661 and its crew traveled the 4 miles to the scene at a speed of 38 knots, arriving on scene about 1:51 a.m. MDTA Police Marine Unit No. 2 was also on scene promptly, a small Zodiac-style police vessel. The collapse had been at 1:29 a.m., and Unit 2 located and rescued J, floating near Pier 20, less than 30 minutes later, at about 1:55 a.m. Because of the possibility of mass casualties, the Sector Command Center for Coast Guard Maryland National Capital Region requested assistance from Station Annapolis in Maryland, the patrol boat Mako out of Cape May, New Jersey, and Air Station Atlantic City in Egg Harbor Township, New Jersey. Other responding agencies included the Maryland State Police, Baltimore County Fire Department, Baltimore City Fire Department, Maryland Department of Natural Resources, as well as first responders from 2 more nearby counties. Responders searched tirelessly for survivors until 8:27 p.m. that day, when the Coast Guard suspended the active search for survivors and transitioned efforts to recovery. Quote, "As the bridge deck collapsed into the water and onto the bow of the Dali, an able seafarer, or AB, who had been on the bow at the time of the bridge collapse, sustained a minor injury while escaping the falling debris. Road worker J was transported by a Baltimore City medic to the University of Maryland Shock Trauma Center in downtown Baltimore, where he was treated for a serious injury." The following day, Wednesday, March 27th, the bodies of 2 of the highway workers were recovered from their submerged vehicle. As the search continued for the remaining workers still unaccounted for, hope was diminishing and frustration was growing. Keep in mind this was all while salvage efforts, investigations, and site securing efforts were ongoing as well. Reportedly, there was up to 8 teams totaling around 50 divers on scene initially. However, it appears once rescue efforts were switched to recovery efforts, the divers did not continue, as the twisted and unpredictable debris was a massive safety hazard. The ongoing salvage efforts were hoped to reveal those victims, still unaccounted for. This was an extremely difficult, dark time for the local community, as it seemed to drag on and on. In the span of about a month's time, quote, between April 5th and May 7th, the bodies of the other 4 highway workers were located. All the victims were found inside vehicles. Autopsy reports for the fatally injured all list blunt force trauma, drowning, or both, as the cause of death. In total, 1 crew member aboard the container ship Dali suffered a minor injury. The road worker inspector escaped physically unharmed. The road worker who escaped his submerged vehicle suffered serious injuries, and those 6 remaining road workers did not survive. The Dali's aberrant trajectory saw it completely avoid Dolphin No. 1, and thus, the ship blasted through Pier 17's fender system, and according to the NTSB, quote, "The estimated impact force of the Dali at the time of contact was over 4 times the capacity of Pier 17. Pier 17 failed and collapsed, resulting in the collapse of spans 17 through 22. Pier 19 collapsed down to the lower intermediate strut, and both intermediate struts on Pier 20 and 21 were destroyed. The piers collapsed down to the approximate level of the water. The strut on Pier 18 sustained contact damage from the collapsing superstructure." Unified Command. In response to this incident, due to the broad scope of potential hazards, which we will discuss shortly, was the immediate establishment of Unified Command, or UC, the NTSB. A UC is a type of incident command used when there is more than one agency with incident jurisdiction. Under a UC, each participating partner maintains authority, responsibility, and accountability for its personnel while jointly managing and directing incident activities. Agencies work together through the designated members of the UC to analyze information and establish a common set of objectives and strategies. In response to this incident, organizations included in the Unified Command were the U.S. Coast Guard, which deployed its Atlantic Strike Team and its Salvage Engineering Response Team, the U.S. Army Corps of Engineers, the Maryland Department of the Environment, the MDTA, Witt O'Brien's, a contracted emergency response company representing Synergy Marine Pte. Limited, the Dali's operating company, and the Maryland State Police. Assisting and coordinating agencies included the NTSB, U.S. Customs and Border Control, the FBI, U.S. Navy Supervisor of Salvage and Diving, or SUPSALV, the Maryland Department of Transportation, the Maryland Port Administration, the Maryland Natural Resources Police, the Maryland Air National Guard, Baltimore City, Baltimore County, NOAA, or the National Oceanic and Atmospheric Administration, the Cybersecurity and Infrastructure Security Agency, the Maryland Department of Emergency Management, the Pipeline and Hazardous Materials Safety Administration, and the U.S. Environmental Protection Agency, or EPA. Inside many of those forwardmost containers impacted by the collapsing structures, crashing down directly onto the ship's bow, were materials considered hazardous like sulfonic acid, corrosive flammable liquids, equipment with lithium batteries, perfumes, alcohols, various nitrous oxides. These were an urgent concern. From the NTSB quote, preventative measures included establishing collection points for spilled material and the use of scupper plugs, sorbent materials, pumps, and hoses to contain any released material. However, quote, no hazardous substances from containers on the ship reached the environment. In addition, another concern initially was a natural gas pipeline known to be roughly 50 feet west of the bridge, running parallel, just underneath the seabed. This buried pipeline allows natural gas to flow to customers on the southwest end of the bridge. Quote, on the morning of March 26th, a responder from the Pipeline and Hazardous Materials Safety Administration notified the NTSB that the pipeline was secure and not losing pressure. On March 27th, the UC contacted BGE, a local gas utilities company, to notify the company that a dive salvage team surveying the damage discovered that the area where the vessel ran aground was close to the pipeline. Later that same day, BGE closed valves on each side of the Patapsco River. On March 28th, the BGE manager of Gas Transmission Engineering told the NTSB that they showed no anomalies after the bridge collapse, meaning presumably it was secured and appeared undamaged despite its close proximity to the incident. NTSB arrival, investigation team established. Rewinding just a little bit back to the immediate aftermath, quote, the NTSB was the lead federal agency for this investigation and learned of this incident from the FBI on March 26, 2024 at 2:16 a.m. NTSB investigators were on scene at the initial incident command post at MDTA's facility by 5:25 a.m. Formal determination of the accident as a major marine casualty was received from the U.S. Coast Guard at 7:33 a.m. A team of 14 investigators, NTSB Chairwoman Jennifer Homendy, and support staff were on scene in Baltimore, Maryland throughout March 26th. The investigative team consisted of specialists in engineering, operations, survival factors, vehicle recorders, and bridge structures. NTSB investigators first boarded the Dali on Tuesday, March 26th, about 7:30 p.m., to conduct preliminary interviews and retrieve VDR data and audio. Parties involved investigating in conjunction with and/or alongside the NTSB included Grace Ocean Pte. Limited, the Dali's owner, Synergy Marine Pte. Limited, the Dali's operator, HD Hyundai Heavy Industries Company Limited, or Hyundai for short, the Dali's manufacturer, the MDTA, the U.S. Federal Highway Administration, the Association of Maryland Pilots, Nippon Kaiji Kyokai, the Dali's Classification Society, or Class NK for short, Maritime and Port Authority of Singapore, the Dali's country of registry. And the NTSB joint investigation would be one that, due to its scope, even I've been struggling with how to describe it for the purposes of this voiceover. Quote, NTSB investigators examined the overall status of the Dali Navigational Bridge, or wheelhouse, to include its overall environment, equipment, and required documentation. The bridge was found to be in order and a functional, well-kept operational workspace. The Dali bow, to include the bosun store and forecastle, suffered severe damage during the casualty, heavily concentrated on the starboard side. The port anchor and chain were indeed paid out. Investigators conducted a visual and operational inspection of the steering gear. The steering gear appeared in good working order and complied with the requirements of Title 33 CFR 164. The next phase of the investigation. NTSB engineers retrieved data during the on-scene investigation using the bridge-mounted USB console, which provided an interface for accessing VDR data. This yielded a 6-hour segment of data centered around the incident. The NTSB continues. Between April 1st and April 29th, 2024, NTSB and Coast Guard investigators, along with representatives from Grace Ocean, Synergy, Hyundai, Singapore, and Class NK, conducted post-accident mechanical and electrical examinations on board to determine the cause of the blackouts. Hyundai technical representatives were on scene as subject matter experts for the vessel's high-voltage switchboard and its physical components. Hyundai also assisted with the equipment changeovers and troubleshooting. To simplify a bit here, the NTSB goes on to explain, with the ship in place, now made safe and powered on, this team of investigators, Hyundai technical representatives, along with vessel crew members, all working together, attempted to, quote, reconfigure the electrical system to the same state as during the initial phases of the incident. So the team performed this troubleshooting by monitoring, for example, the diesel power generators, the emergency generator, the high voltage step-down transformers, the high and low voltage breakers, the high voltage, low voltage, and emergency switchboards, along with other relevant systems. By April 10th, roughly 2 weeks on, examinations, quote, were concluded without resolution or confirmation of what caused the initial underway low voltage blackout. The fuel issues or contamination question. By April 11th, fuel sample test results came back confirming that there were no issues or concerns with the quality of fuel the Dali had been using the night of the impact, and thus, fuel contamination or fuel issues in general were ruled out. We have a lot to cover, so if it seems like I'm being succinct for some of these items, it's because I am intentionally. The items ruled out, we need to get through so we can get to why this happened. Emergency generator. So why didn't the emergency generator help in preventing the low voltage blackout or recover emergency power more quickly? From the NTSB. After a loss of low voltage power, the emergency diesel generator is designed to start and power essential onboard systems, such as navigation and communication equipment and emergency lighting. After the initial underway blackout, the Dali's emergency diesel generator took 70 seconds to connect, more than a full minute. We found this was because the generator damper actuator's limit switch, which detected whether the damper was open or closed, did not indicate open in the required time due to unknown circumstances. Due to the system design, any delay in the opening of the radiator damper, or its limit switch indicating it as not open, would postpone the emergency generator starting. The NTSB points out in their italicized footer text that this was some type of louvered vent that allows or hinders airflow through the engine's radiator for cooling, and that sensors attached to it detected those louvers were closed initially when the emergency diesel generator would have otherwise kicked on immediately, automatically. The NTSB also points out in this footer text, quote, during post-accident testing, the chief engineer reported that no work had been done on the emergency diesel generator, emergency switchboard, or associated equipment after the accident. Presumably this implies the state investigators found this equipment was unchanged from when the key bridge incident occurred. One loose signal wire. From the NTSB. On April 12th, without pre-alarm or warning, the vessel experienced another low-voltage blackout, similar to the initial March 26th blackout, the blackout that caused the vessel to lose control. 10 days later, quote, a third envoy of engineers from Hyundai arrived to restart troubleshooting efforts alongside investigators. After ruling out fuel issues, the high voltage and low voltage power paths, like breakers and transformers, yet still getting seemingly random and sudden blackouts similar to the night of the incident, quote, Hyundai engineers then conducted point-to-point signal wire checks and discovered an inadequate or loose connection in the circuit. More specifically, they discovered inside the control panel or cabinet, one of the wires labeled 381, going in the terminal block 381, was physically loose, which we will cover in more depth. But to oversimplify, in modern automated systems, like much of the Dali's power generation, propulsion, and control, the digital communication signals sent to and from these pieces of machinery are crucial to their continued operation. These signals aren't just digital ones and zeros that get passed through a computer controlling everything. A computer and its automation programming likely receives and sends signals, but they almost always pass through what is referred to as the control panel, or cabinet, physically via signal wires, each wire assigned to a specific signal. I'll use my days in a past life of robotic systems engineering and automation integration to try and draw a high-level overview and hopefully help familiarize viewers with low-voltage signals in automation. When you have, for example, a robot that stacks boxes on a pallet, the system appears to all be working in unison, with a conveyor bringing in boxes, another conveyor bringing in pallets, and the robotic arm grabbing each box and stacking them in a pattern, until you have an entire pallet of boxes ready to be stretch-wrapped and sent on its way. However, this system is all working on a basis of dozens, hundreds, sometimes even thousands of physical signals all being sent and received as specific conditions are met. The main computer controlling this system, the one in our example, with all the programming and processing power needed, in this case, it's the robot controller. It's like the brain of the system. It can send programming directly to the robotic arm, but the other machinery in the system isn't nearly as capable, or in many cases, may not be compatible with that programming language. The conveyors, for instance, may have only forward or back, start or stop, and are produced by a completely different company. The user interface for operators to engage with may have very easy-to-use instructions, like buttons programmed to run, pause, or stop the whole system. The fencing around the system to keep people safely out of the working area may have a gate that simply triggers an emergency stop if open during operation. These signals to or from physical pieces of machinery are sent via low-voltage wires that are networked, or all pass through a central cabinet the NTSB calls in the Dali's report a control panel, or switchboard. In our example, if the robot controller is like the brain of the system, the cabinet, full of dozens or hundreds of wires, is like the spine, and all the other moving parts receiving signals are the appendages. And I preface this next part by saying, do not attempt in any situation. Let's say while our hypothetical system is in operation, the conveyors are moving, the robot is in motion. That fencing gate suddenly gets opened by an operator. The signal now gets interrupted. The system goes into emergency stop and can't be reset until the signal is restored. Or, if I were to leave that gate closed and secured, but instead opened the cabinet and disconnected the same corresponding signal wire, in this instance, one of the wires labeled S24V, we would get the same result. The system would go into emergency stop and remain in that state, and we wouldn't be able to even reset it until the signal is restored. This is not to imply anything similar to this sequence of events took place on board the Dali. The goal of this explainer is to try and help viewers understand the importance and functionality of low-voltage signals in automated systems. Back aboard the Dali, investigators established this loose connection as initial cause of the cascading blackouts. However, establishing that this wire came loose in the first place also involved an incredibly thorough and intricate understanding of automation signals and systems, down to the seemingly microscopic level, at least when compared to the outsized impact it had. First, investigators found inside the cabinet, the signal wires had been installed in the corresponding terminal blocks with their labels covering the blue plastic ferrule collars. I realize this may sound like a word jumble. I will attempt to explain as we continue. When I was in robotics and automation, our lives revolved around these boxes full of what may look like an absolute mess of cables, colors, and switches. Like I said, a kind of spine, with the nerves of the system all passing through this central stem, if you will. It was in our training to specifically install these in a manner that left the heat shrink label back far enough from the ferrule on the end so that the connection into the terminal block could be seen clearly. I dug through my old Pelican box, my travel toolbox, and scrounged up a few items I could use to demonstrate what each item is here. The heat shrink label, mine doesn't have a number printed on it yet. the ferrule that goes on the cleanly stripped end of the signal wire, and a couple terminal blocks. Green for ground and gray for everything else. However, I did not have any terminal blocks on hand at first, so I tried a local supplier and they stated they haven't been stocking that exact style of Wago terminal block for quite some time. I do remember seeing that exact shape quite often back when I was still in the industry, which was many years ago, for what it's worth. So I grabbed the closest analog the local distributor could supply me with, the two I have here, which is still a push-type DIN rail terminal block, allowing me to at least give you guys a visual here. Just keep in mind, these terminal blocks would normally be installed along the DIN rail of the cabinet already, labeled accordingly and firmly in place prior to installing the signal wires. Demonstrating in this way here at my desk, I can show the inner workings of a spring clamp block, roughly similar to the NTSB images here in the report. The NTSB continues. Further troubleshooting led engineers to discover a loose signal wire on terminal block 381. High voltage breaker 1 needed a constant signal informing what's called its undervoltage release device. Quote, when the wire plugged into terminal block 381 became loose, the electrical pathway to the undervoltage release device was interrupted, and the device de-energized. This led to an unintended trip of high voltage breaker 1. However, even with the tripping of this breaker, and throughout the blackout incident, no alarms or warnings specifically indicating this issue were initiated by the system. The NTSB continues. When the wire became disconnected and the high voltage breaker opened, it was as if an operator had rotated the breaker control switch to open, causing the breaker to intentionally open. Therefore, the vessel's power management system, which typically registers alarms when conditions are abnormal, did not initiate warnings or alarms when high voltage breaker 1 opened unexpectedly, because it did not sense any conditions that fell outside safety parameters. After reinserting wire 1 into terminal block 381, the engineers closed the breaker successfully. Hyundai Heavy Industries engineers then disconnected wire 1, resulting in high voltage breaker 1 opening or tripping, causing a vessel blackout similar to the initial blackout on the accident voyage, including no warnings or alarms. And from Hyundai Heavy Industries' own report, they concur, stating, quote, the most likely cause of the initial blackout was a loose signal wire in the high voltage switchboard that was not firmly connected to its terminal block. The loose signal wire subsequently opened the vacuum circuit breaker, high voltage breaker 1, disconnecting the step-down transformer 1, from the high voltage switchboard, resulting in an outage at the low voltage switchboard. At the time, the vessel was utilizing diesel generator number 3 and 4 and step-down transformer 1. The outage shut down the auxiliary electrical pumps required to keep the main engine and generator engines running. As a result of the first outage in the low voltage switchboard, the main engine shut down and the vessel lost propulsion. Records indicate that there were no attempts to restart the main engine after the first recovery. Returning to the NTSB report, the NTSB concludes that the position of the wire label banding on the ferrule of terminal block 381's wire 1 prevented wire 1 from being fully inserted into the terminal block spring clamp gate, causing an inadequate connection and leaving wire 1 loose and vulnerable to becoming electrically disconnected. The NTSB points out that this signal wire was only intermittently making contact due to that lacking connection. I've placed another label over the end of my ferrule here at my desk, and you can see how it might obstruct the installation process. This is a slightly different style of Wago DIN rail terminal block than what's referenced in the NTSB report, keep in mind. If I clamp it at the very end and apply pressure to try and pull it out, I'm not actually able to get the ferrule to release from the clamp, even when hanging on by just the very end. Similar in principle, like push type and spring clamp, but slightly different in its shape and mechanical action. However, it could be that even still connected, barely hanging on, yet pulled back too far, meant that style of terminal block doesn't carry the signal due to a lacking connection. I'm not sure. Anyway, the NTSB points out arcing damage that investigators found inside the gate, which to me is the most telling of an intermittent electrical signal. Even low voltage will arc somewhat if the connections are reaching through a slight gap between them. And low voltage on this vessel was 440 volts, so it's to a different standard on board ships like this. Quote, if infrared thermal imaging had been used to inspect wire connections within the high voltage switchboard before the accident as part of the Dali's preventative maintenance program, the loose signal wire may have been identified. And the NTSB provides example images of what this imaging looks like. This, however, only explains the importance of the wire in the control panel, the breakers tripping, and the low voltage blackout. But regarding how and why the propulsion, steerage, and other major systems couldn't or didn't recover in time, or resulted in a total loss of control, I've reached out to Chief Makoi again. You may remember his clips also added context on our marine electric video. He has experience as a chief engineer with systems like these aboard similar vessels.
The next finding focused on the flushing pump, a piece of equipment that was never intended to support critical ship operations. From my own experience, especially working with Hyundai Himson engines, the same type installed on Dali, flushing pumps have a very specific purpose: flushing fuel lines during maintenance or when switching fuel grades. They are small, temporary use pumps. They are not designed to supply fuel to generators during normal operation. That job belongs to the dedicated fuel supply and booster pumps, systems designed with redundancy, automation, and sufficient capacity in mind. But on the day of the casualty, that wasn't how the system was running. The flushing pump had become the primary source of pressurized fuel for diesel generators 3 and 4, the generators that were powering the ship at the time. So instead of a properly engineered, fault-tolerant fuel system supporting the power plant, the ship's operation was relying on a maintenance pump never meant for critical service. And that decision mattered. The flushing pump had no redundancy, there was no standby pump, no automatic switchover, no protective logic, and importantly, no automatic restart after a power loss. So when the first blackout occurred and low voltage power was lost, the flushing pump stopped, and it stayed off. With insufficient fuel pressure, generators 3 and 4 shut down, leading to the second blackout, affecting both the high and low voltage systems. When the 440 volt bus was reconnected, there was a sudden surge of power demand due to some of the essential machinery automatically starting up. This meant that the generators needed more fuel immediately in order to compensate. But since there was no pump supplying fuel, only gravity, the generators were in a way overloaded, starved of fuel, and started losing speed, eventually hitting the low frequency, which will cause the engines to trip, thereby causing the second blackout, which, as shown in my previous video, originated from the generator breakers. What makes this even more concerning is that the ship had already experienced 2 blackouts the previous day due to the exact same issue while still in port. Yet the vessel sailed without addressing it. The investigation concluded that while this pump configuration did not cause the first blackout, it severely impaired recovery. The system relied on perfect timing and manual intervention to restore fuel pressure, and in blackout conditions, that's not just impractical, it's unsafe. And perhaps the biggest lesson is this: this wasn't an isolated mistake. Apparently, the same setup was found on at least one other vessel in the same fleet. A workaround, likely intended to be temporary, eventually became standard practice. Sad to say, this was an operational oversight, and as much as NTSB doesn't want it to appear as human error in their report, it clearly is. It's a classic issue of we've always done it this way.
I'll have Chief Makoi linked in description and pinned comment if you'd like to check out his Dali videos for more context. From the NTSB. As a result of our investigation, we identified 4 safety concerns that, while not causal to the initial underway blackout, were related to preventing a loss of propulsion and recovering steering and vessel electrical power following a blackout. the configuration of the main engine to shut down due to low cooling water pressure, the use of the flushing pump as a fuel service pump for the electrical diesel generators, the operation of the vessel's low-voltage step-down transformer high-voltage breakers in manual mode rather than automatic, the effect of emergency diesel generator radiator damper positions on the generator's ability to start. Regarding that maintenance blackout caused by an exhaust damper being mistakenly closed while in port Monday, March 25th, the day before the Dali would get underway, I asked Brick Immortar's own AB Michael to weigh in. Michael is aboard cargo ships regularly, cargo ships that spent a lot of time performing cargo operations in port and performing a lot of maintenance prior to getting underway. Quote, "Human error is human error, and there's no way to fully remove that from any part of this industry. It all comes down to knowing the equipment you're working with and the quirks associated with it, be it in any department, deck, bridge, or engine. The maintenance blackout was something that obviously shouldn't have happened, but is also something that isn't totally unheard of, especially if a newer / less experienced crew member was the one working with the exhaust damper." Unquote. While the NTSB doesn't make any direct connection, at least that I can find in their report, between the in-port blackouts and loose signal wire blackouts, it's important to note that the NTSB's in-port blackout section in their report does point out that same flushing pump playing a secondary role there as well. Quote, "When power was restored, certain auxiliary pumps restarted automatically, according to their design. But the flushing pump was being used to supply fuel for the diesel generator that had just come online and required a manual restart as designed. The diesel generator ran for about 5 minutes. Before the crew could manually restart their flushing pump, the generator's speed began to decrease due to insufficient fuel pressure. The decrease in speed caused the generator to underperform, causing the second full vessel blackout on Monday, March 25th. Harbor tugs. Questions also swirled around how and why harbor tugs wouldn't have either A, been attached and helping to maneuver the Dali all the way through the ship channel until reaching the mouth of the harbor, or B, at the very least, escorting alongside nearby the container ship and available to help in an incident like this. There are documents in the NTSB's docket, like an email investigators sent to the company that owned tugs Eric and Bridget McAllister, those two tugs that helped usher the Dali away from the Seagirt pier and into the ship channel. However, it's important to note the email purpose appears to more or less verify company procedure, answer questions regarding physical limitations, safety minimums and maximums, and define terms like ship escort versus tethered escort, and so on. The overarching knowledge investigators are working from in the first place is that, from the NTSB, quote, "In the port of Baltimore, it was practice to let go of the tugboats used in maneuvering when the vessel was steady in the Fort McHenry Channel, barring any extenuating circumstances that would compel the pilot to retain the tugboats. Furthermore, tugboats not classed as escorts needed to be let go before the vessel they were aiding reached a speed that exposed the tugboats and their crews to greater risks, while operating in the vessel's wake and areas of low pressure near the hull." Which still leaves the bigger picture questions on the table as to why it would be common practice to have the tugs let go once in the ship channel in Baltimore Harbor versus remaining tethered all the way through like they would in, say, a tighter, more challenging harbor. I've reached out to Tim B. at Sea, a seasoned maritime and tugboat expert, as he's made a couple videos explaining this and more in detail.
So here's a chart of the Long Island Sound, and here is the New Haven Sea Buoy and the entrance into New Haven. See, the ships go all the way up here and there. And right there, that's the little sea buoy there. That's where the ships will come in. They'll line up on the sea buoy, and they'll start running into the channel like this and go through the breakwater, turn a little bit, and head over to what we call the dog leg, and then get in there. But when you zoom in on the chart, what you'll notice is that they don't have a lot of water. 14, 11 feet, 10 feet, and all that sort of stuff. And these ships are drawing 35, 40 feet of water that come in there. So it's really tough, and it's so skiddy that there's no meeting or passing. So in other words, you don't have an inbound ship at the time with an outbound ship that you might somewhere else. So in a situation like this, if they lost power or something like that, if they dropped an anchor, you might notice that there's a buried cable underneath that runs power over to Long Island, and so that's probably something they don't want to do. And another thing is that they don't have a lot of room here. So in other words, the channel is so small they don't have a lot of sea room to maneuver. So they'll put a tug up on the one side of the bow and put a tug up on the other side of the bow, and sometimes they'll even have those tugs running in reverse while the ship is pushing against it, so that the ship can still have water going across its rudder. But let's get back to the Port of Baltimore. So if you see down here in the lower right-hand corner, that would be the channel that we were actually coming into. We were at the other end of this channel when all this happened. We were taking a load in underneath the Key Bridge and going to take a left under the Key Bridge into Curtis Bay, and that was where our destination was, right over here. This is set up much differently. To give you an example, this is where the Dali was berthed and was loading and unloading, and she came off with two tugs that had actually just those two tugs had actually just sailed another ship. And that's kind of important to know, so that if you say, well, you just should have tugs, well, you're going to have to build a lot more tugs and pay a lot more people and all that sort of stuff. But anyway, these two tugs were alongside the ship as it came around here, and then once they got it lined up on the straightaway, the tugs were released, and this is very standard. This is not something that they let it go too early or anything like that. This is very common. It's a straight shot from here, so the ship will be under its own power, and once it starts making way, it will have good steerage, and the tugs might have another job to go to. I think it's also important to say, we all know what happened when it hit the bridge. We've all seen the videos 1,000 times, but I really think it's important for you to understand that even if those tugs were there, once they pull it off the ship, they're just running along so they can give it a bump if something goes wrong. And that's kind of just a push. Well, the idea of having a line tied off to them like they do in New Haven would really slow things down. And it just doesn't make sense, because out of all these years, this has never happened, because it's just happened on this particular time, and it was a terrible tragedy and all that. But if you had a 5,500 horse tractor tug up in the bow on the south side or on the starboard side of the ship, and the ship started taking a dive, he'd probably do everything he could. But between 7 and 8 knots, 100,000 ton ship turning into it, he's not going to be able to have the same pushing power he would if he were at the dock and the ship was at a standstill. When he's going, even though it's a tractor tug, you just don't have that much control. I mean, like, for example, our tug and barge is about 5% of the tonnage that this is, and if I'm moving at 3 or 4 knots, a tug will come in and push on the side of me, and it takes a long time before anything starts to happen. You get a 100,000 ton ship moving at 7 some knots, and no tugboat, no assist boat is going to be able to stop that. And some of you guys say, well, maybe it's going too fast, we should slow it down. Well, a lot of these ships, remember, they don't have a reduction gear, they don't have any sort of transmission, and so when they're clutch ahead, their slowest speed is usually right around there, so they were probably going as slowly as they could. To put this in context of something that we can all kind of think about, we all know how big an aircraft carrier is, and displacement-wise, and how big this thing is, it's about the size of an aircraft carrier. And people will tell me, oh, I see in the comments this, I see aircraft carriers, I see ships being moved all the time, tugs can move these ships. Yes, we can move these ships. What happens is we move these ships when they're at a standstill or very slow. And when we are moving, like I tried to explain what happens when we go into New Haven, those are only there for braking the ship so that the ship can keep working ahead and have more water going on the rudder so that they still continue to have steerage as they're going. Now, there is one possibility. There's one thing, and that's that if you didn't have tugs on the bow, but you had a stern tug, a great big tractor, an enormous tractor, once again, adds a lot to the money and all that sort of stuff, yeah, you could slow he could slow that thing down. But once again, everyone I've talked to and that agree with me that, in the industry think that all it would have done is slow it down, but the damage probably still would have happened and the bridge probably would have come down. If it didn't come down, it would be totally messed up anyway. And so I just need to tell you guys, tugs are not the answer. Quite frankly, if they put tugs on everything, it's going to be great. We don't have the tugs or the personnel. In fact, we don't even have the personnel to run tugs today. So, with the tugs that we have. There's another thing that I think everyone's forgetting when they say, we got to do this, we got to do that. Had the Dali gotten through the bridge there, had it done that, it still has to get under the Bay Bridge. Are you going to have the tugs go all the way to the Bay Bridge? Some people have even suggested taking tugs all the way to sea. That would tie up 2 tugs for almost 2 days. They'd have to go all the way out to sea and then come all the way back to get the next one. Do you know, we would have to build so many tugs and have so many people to do that. And once again, I don't think it matters, because I don't think that would have stopped what happened.
I'll also have Tim B at Sea linked in description and pinned comment if you'd like to check out his Dali videos for more context. Increasing vessel sizes and traffic density in U.S. ports. From the NTSB, we investigated the wider issue of large containerized cargo ships, which have grown significantly in size and capacity in recent decades, calling more often at ports such as Baltimore. The increased size of vessels and increased cargo volumes presents challenges for existing port infrastructure that may not have been built with consideration of the larger vessels and greater traffic density. We found that increasingly larger containerized cargo vessels, such as the Dali, pose increased risks and challenges to maritime safety due to their reduced maneuverability in proximity to existing port and waterway infrastructure that was not designed to accommodate vessels of such size. We also found that as cargo vessel designs continue to evolve with the latest available standards and technology, increased redundancy to maintain critical systems, such as the main engine and steering, can mitigate risks in restricted waters. An example of a bridge with more robust pier protection than was present at the Key Bridge is the Sunshine Skyway Bridge near Tampa Bay, Florida. The main piers are protected by islands, whereas the 5 approach piers on each side of the main piers are protected by a dolphin system. The use of dolphins to protect the high-level approach piers was a result of a risk analysis, which indicated that the high-level approach piers were vulnerable to a catastrophic vessel contact. The 60-foot diameter dolphins were designed to withstand a contact from either a loaded 23,000 deadweight tonnage or an empty 87,000 deadweight tonnage bulk carrier. The 54-foot by 4-inch diameter dolphins were designed to withstand an impact from a loaded 25,000 deadweight tonnage barge or an empty 70,000 deadweight tonnage vessel. The 47-foot diameter cells were designed to withstand impacts from a loaded 15,000 deadweight tonnage barge or an empty 35,000 deadweight tonnage ship. All design impact speeds were 10 knots. The sheet piling was driven through a sand overburden 10 to 40 feet thick, and then 5 to 10 feet into a stiff limestone stratum known as the Hawthorne Formation. For their part, MDTA and the City of Baltimore responded to the NTSB's findings. Just to note, I've selected this post from MDTA's Facebook page, dated March 21st, 2025, a year after the incident, as it summarizes much of their press statements and interviews with news outlets. Quote, "The MDTA is reviewing recommendations made by the NTSB. The MDTA maintains the catastrophe and the tragic loss of life was the sole fault of the Dali and the gross negligence of her owners and operators, who put profits above safety. As requested, the MDTA will provide an update to the NTSB within 30 days, which will include any action we intend to take based on our active evaluation of the pier protection systems, operational changes, and vessel transit procedures of the Bay Bridge. The evaluation is being conducted using American Association of State and Highway Transportation Officials methodology and was underway when the NTSB requested its results last fall. Over the past 50 years, hundreds of thousands of vessels transited under the Key Bridge without incident. The Key Bridge, like other bridges in America, was approved and permitted by the federal government in compliance with those permits. The safety of Maryland highways and bridges is always a top priority for MDTA. Over the last 10 years, the state of Maryland has spent more than $175 million on safety and security for the Bay Bridge alone. MDTA is committed to evaluating and implementing operational changes and vessel transit procedures for both the new Key Bridge and the Bay Bridge. The Bay Bridge MDTA is referring to here is the even larger Chesapeake Bay Bridge, or Governor William Preston Lane Jr. Memorial Bridge, roughly 18 miles southeast of where the original Key Bridge once stood, which carries Highway 50 east and west across the Chesapeake Bay over another major shipping lane. Recommendations marked urgent by the NTSB. To the U.S. Coast Guard and the U.S. Army Corps of Engineers, support the Federal Highway Administration in establishing an interdisciplinary team, including representatives from the Federal Highway Administration, U.S. Coast Guard, and U.S. Army Corps of Engineers, and provide guidance and assistance to bridge owners on evaluating and reducing the risk of a bridge collapse from a vessel collision. 2. An entire paragraph of city, county, state, and others who oversee, quote, bridges over navigable waterways frequented by ocean-going vessels with unknown levels of risk of collapse. Calculate the American Association of State Highway and Transportation Officials Method 2 annual frequency of collapse for the bridges identified in this list we'll cover shortly, for which you are responsible, and inform the NTSB whether the probability of collapse is above the calculated threshold. And Method 2 in this instance essentially, quote, determines the annual frequency of collapse, or AF, which is the probability of a bridge collapse due to vessel collision in 1 year's time. Quote, if the calculations that you performed in response to NTSB safety recommendation H-25-3 indicate that a bridge has an annual frequency of collapse greater than the calculated threshold, develop and implement a comprehensive risk reduction plan that includes, at a minimum, guidance and assistance from the interdisciplinary team identified in safety recommendations H-25-1 and H-25-2, and implement short and long-term strategies to reduce the probability of a potential bridge collapse from a vessel collision. Some of those states referenced for review, at least those bridges marked critical/essential, include California, Florida, Illinois, Louisiana, Maryland, Massachusetts, Michigan, New Jersey, New York, Ohio, Oregon, Pennsylvania, Texas, Washington, and Wisconsin. And we will cover the NTSB's probable cause in a moment, but a key item I've changed in production is moving what we've nicknamed the legal aftermath of these incidents, which includes financial aftermath, along with the long rambling safety recommendations read in full. Those are becoming Patreon exclusives. I'll explain. The previous video on fishing vessel destination was my first official attempt at this, and it went way better than I'd expected. It actually allows me to get these videos published sooner. Much of the legal stuff can be speculative, controversial, or simply conjecture, since it's much more difficult to dig up, and sources tend to be less reliable. So moving it to a Patreon exclusive frees us up to report on it more openly. That and the authorities who investigate these incidents tend to be very long-winded in their full list of recommendations, so I've chosen to start only summarizing them or pointing out those most urgent in the main video release. Probable cause. The NTSB determines that the probable cause of the contact of the container ship Dali with the Francis Scott Key Bridge was a loss of electrical power, or a blackout, due to a loose signal wire connection to a terminal block stemming from the improper installation of wire label banding, resulting in the vessel's loss of propulsion and steering close to the bridge. Contributing to the crew's inability to recover propulsion from the loss of electrical power was the limited time available due to the Dali's proximity to the bridge. Contributing to the collapse of the Francis Scott Key Bridge and the loss of life was the lack of countermeasures to reduce the bridge's vulnerability to collapse due to impact by ocean-going vessels, which could have been implemented if a vulnerability assessment had been conducted by the MDTA as recommended by the American Association of State Highway and Transportation Officials. Also contributing to the loss of life was the lack of effective and immediate communications to notify the highway workers to evacuate the bridge. They continue. In lieu of police officers or highway workers charged with traffic control and capable of quickly stopping traffic, A motorist warning system designed to warn and stop motorists from entering onto a bridge is a possible countermeasure that can be quickly implemented to save lives and may be a component of an effective bridge protection strategy. Owners of bridges over navigable waterways frequented by ocean-going vessels would benefit from updated guidance on motorist warning systems, including incorporation of hazard alert and sensing technologies capable of detecting errant vessels and bridge movements that would indicate a need for bridge closure, and systems that would both warn and prevent motorists from entering a bridge once a threat is detected. Had the inspector and highway workers been notified of the Dali's emergency situation about the same time the MDTA police officers at each end of the bridge were told to block vehicular traffic, the highway workers may have had sufficient time to drive to a portion of the bridge that did not collapse. Effective and immediate communication to evacuate the bridge during an emergency is critical to ensuring the safety of bridge workers. Demolition, salvage, and clearing of debris. From the NTSB. The U.S. Army Corps of Engineers, Baltimore District, which operates and maintains the Fort McHenry Channel, worked with the U.S. Navy Supervisor of Salvage and Diving to facilitate salvage and debris removal from the Fort McHenry Channel. SupSalv would lead the following team of contractors to make this happen. Don John Marine provided pollution salvage and heavy lift support, such as cranes and barges. Emergency ship salvage and marine provided survey boats and operators to survey the area using sonar equipment. Resolve Marine served as the vessel salver, and Skanska served as the MDTA's non-navigation channel response team. Quote, "The bridge strike and subsequent collapse resulted in steel and concrete wreckage and debris falling into the Patapsco River and blocking the channel and all ship traffic into and out of the port. On May 13, 2024, salvers used explosives to remove sections of the collapsed bridge from the Dali. Salvage crews ultimately removed about 50,000 tons, equivalent to about 100 million pounds of material from the riverbed. On May 20th, 2024, the Dali was refloated, removed from the channel, and returned to Seagirt Marine Terminal to offload cargo and additional debris. After the Dali was removed from the channel on May 21st, the Unified Command created a limited access channel to allow vessels to enter and leave the Port of Baltimore. The limited access channel had a depth of 50 feet, width of 400 feet, and vertical clearance of 214 feet. On June 4th, the last large piece of steel truss was removed from the federal channel. On June 10th, the Fort McHenry Channel was reopened for vessel traffic. In closing, all too often we see practices and methods in the workplace that, quote, got us this far, or that's just the way we've always done it, yet turned out to be the weakest link in the Swiss cheese model of catastrophic failure. The alleged loose signal wire being a manufacturing and installation issue was likely not something crews aboard the ship interacted with on a regular basis. But the practice of using the flushing pump as the primary service pump, from the NTSB, quote, was inappropriate because the necessary fuel pressure for diesel generator 3 and 4 would not be automatically reestablished after a blackout per the fuel system's design. Along with the emergency diesel generator's failure to connect and power the emergency switchboard within 45 seconds, as required by International Maritime Organization regulations due to, quote, the radiator damper actuator's limit switch not indicating open in the required time due to unknown circumstances. Unfortunately, in so many cases, it's only when the Swiss cheese model lines up and catastrophe ensues that these practices get put under the spotlight. The other 99% of the time, when we're just trying to get through the day, reach the next destination, meet the quota, complete and close out the work order, the fatigue of the routine can be one of the most difficult and often imperceptible obstacles to overcome. But the motor vessel Dali wasn't the only party investigators held to account. There's a reason why motorist warning systems are one of the most viable solutions at this point in time, in my opinion. The world of petroleum, container, and cargo shipping, the global supply chain has moved on, seemingly decades ago, while many countries like the US are currently entrenched in a system of infrastructure built for an age that no longer exists. This betrays a long-term complacency that can feel almost impossible to escape at this point. Infrastructure improvement, revitalization, and/or complete renovation almost always appears at first glance to be prohibitively expensive. But should we be looking at public works like these through the lens of monetary profit or loss in the first place? You may not be someone who frequents an area with bridges like the one previously over Baltimore Harbor and say to yourself, my area doesn't have huge ships traveling underneath our roads. But does your area have freight trains overhead on aging overpasses? How about neglected infrastructure underground? Do sinkholes sound safe at 45 miles per hour? How about potholes large enough to blow out the tires on the 70-foot-long, 80,000-pound big rig doing 60 miles per hour right next to you on the highway? Have personal vehicles decreased in size and weight over the last few decades? What was the average passenger vehicle weight when some of those old stretches of road were originally engineered? It's all infrastructure, from the potholes to the Francis Scott Key Bridge. How long can those responsible say, not my problem, to any of these examples? Months? Years? Decades? A century? A developed country tends to foresee these issues and make long-term adjustments accordingly, for the good of society. Infrastructure being allowed to fall behind on what starts to feel like such an insurmountable scale can be one of the telltale signs of a country truly unable to face the reality of a world moving on. Thanks so much for sticking with Brick Immortar. All the viewers, the likes, the subscribers, it encourages me and helps the channel more than I can put into words. But on a side note, a quick yap if you will. Researching for this project and in general, just understanding this incident, like many others on this channel, took me on countless unexpected twists and turns. I had no idea I'd be able to demonstrate the loose signal wire and terminal block using my old tools, for instance. Nor did I expect to discover that the road crew inspector ran for his life as the bridge crumbled directly behind him, like something out of an action movie. I do run into this sort of thing a lot lately, especially as I continually refine my research and writing process. What I mean by run into is the rewrites, the double, triple checking of information for accuracy, and on and on. We are entering an age where I personally feel the responsibility to prioritize facts over feelings, accuracy over haste. A redundant reality check-based, thoroughly human-worked process over becoming a content farm is crucial now more than ever. It is incumbent upon all of us to continue pushing the importance of experts in their field over zealots in their ideology, hard-won experience and lessons learned over self-profit vibes and vapid know-it-allism, thorough investigation and fact-finding over incompetence, nepotism, and cronyism. I truly believe maintaining or creating safer communities and workplaces requires cooperation, compassion, and critical thinking. I'd like to express a huge thank you to those supporters who stick by Brick Immortar even when these videos take so long in production. And a special thanks goes out to those top-tier supporters on Patreon. Aaron M., Alex S., Andrew F., Anna B., Anthony, Blake BMW, Bonesaw 7590, Brendan C., Brendan A., Broken Spectrum, Calliope Cleopatra, Carolyn, Chaz B., Christian T., Dagger Farmer, David M., Elijah C., Emma V., Eric M., Forrest W., Giant M., Grumman Cat, Hank H., Heyman Taylor, Hazmat Unit, Hunter B., Isaac H., Jenica S., Joshua S., Justin S., Kyle W., Library of Scars, Lisa J., Lucas T., Manuel M., Mark W., Matt W., Maxim K., Maximum Hats, Meg T., Megan M., Michael M., Neil Cunningham, Owen W., Paris Synthesis, Paul Rorba, P. Rush, Paul Z., Peyton, Philippa A.L., Rats and Lab Coats, Robert G., Sawyer A., Scott H., Scott P., Someone on Earth 598, Space Cadet and Operative Gamma, Storm S., The Handkerchief, Tristan B., Vlad B., Woods Wolf, Wyatt C., and Yvonne R. And don't forget, your safety matters.